All right, we're back again after many months again. I'm sorry, I'll try to make these more consistent. It's just when you start a new job and you move around and things happen, but we're back. Let's go. So we're back with some hydraulics. So first question, how many days are required to drain a 500 million gallon reservoir with an outlet pipe capacity of 100 cubic feet per second? All right, so two things we got here, a volume and a volumetric flow rate. And we want how many days it'll take to drain that reservoir. So to solve this, we're gonna use a very simple formula, and that is going to be time equal to V over Q, which is our volume over our volumetric flow rate. And as you can see from the question, we have both of those. So we can go ahead and solve. That's gonna equal, got 500, I'm gonna write it like this, million gallons. And so our flow rate, we were given 100 cubic feet per second. So we have the volume right now in gallons, and we want to know how many days. So we're going to have to convert both cubic feet to gallons and seconds to days. So let's go ahead and do that. We got 100 cubic feet per second. Convert that to gallons first. That'll be 7.48 gallons per cubic foot. Now have this unit conversion memorized. I mean, if you go into any like water resources field or anything, probably going to use this one a lot. So just have this memorized, going to save a ton of time. All right, so we have that converted. So now we need to convert seconds to days. We got 60 seconds in a minute, 60 minutes in an hour. Finally, we'll try and squeeze in. Hopefully I'm not blocking. No, my stupid face cam in the way. Don't want to block that. 24 hours in a day. So there we go. We'll just plug and chug that through, and we should hopefully get 7.7 days. Oh, terrible circle. Using a new thing here, so I gotta get used to that. And by the way, if I make any mistakes in here, please comment, let me know. That would be a little awkward. You know, so please just let me know. Try to act like I know what I'm doing, but sometimes things slip. Okay, so that's first one done. All right, so we got our second question. So it is use the Darcy-Weisbach equation to estimate the head loss through a 4-foot diameter, 5,000 foot long concrete pipe that conveys 75 cubic feet per second of 50-degree Fahrenheit water. All right, so right off the bat, they tell us what equation to use. How nice of them. So let me write that down. So the Darcy-Weisbach equation is that head loss is equal to friction factor F times length over diameter times velocity squared over 2 times gravity. All right, so what do we got so far? We do not have the friction factor F. We have the length, we have the diameter, we know G, and we don't know the velocity, but we do have the flow rate, so we can use the continuity equation, Q equals V times A, to find that. So let's do that first. We got Q equals VA. We'll convert that to V equals Q over A. That will be, we have 75 cubic feet per second to find the area. Pi over 4 times, we got 4-foot diameter squared. That'll be 5.97 feet per second. All right, so to find that friction factor F, we need a couple things. So we're gonna have to use this MOODy diagram in order to find our friction factor F. So first thing is we need to find the Reynolds number. And on this picture that I found, it was the very first picture I found, it does have a Reynolds number equation, but we're gonna use a slightly different one. All right, I had to erase everything, I'm sorry, but we need space. So the equation I'm thinking of using is actually this one. So we got Reynolds number equals diameter times velocity over kinematic viscosity. So if you go to page 200 of your FE reference handbook, you'll find properties of water there, and you see in our question they gave us that the water is 50 degrees. So if you go there, you'll see that water is 50 degrees. The kinematic viscosity of water is 1.41 times 10 to the negative 5 feet squared per second. And we already had diameter and velocity, so now we can plug that in to find our Reynolds number. We got 4 foot times 5.97 feet per second over 1.41 times 10 negative 5 feet squared per second. So plug and chug. So we get something like 1.69 times 10 to the 6 for our Reynolds number. All right, I'm gonna erase that because we need just one more thing, a fun eraser. So you can see here on the y-axis, we need relative pipe roughness, and you can barely see this equation for it. But to get that, it's this roughness factor over the diameter. So in the question, we got that it was a concrete pipe, and for that, the roughness factor is going to be 0.001 feet, and we know the diameter to be 4 feet. So we get that to be 2.5 times 10 to the negative 4. And I'm just showing you here real quick. You can find on page 201, you can find that Reynolds number equation that we used here, and our MOODy chart, and also that roughness factor right here. And this is where I got that number. So in hindsight, I should have used the MOODy diagram from the actual reference handbook I've been using, but you know, live and learn. So we have both of the numbers we need to find our friction factor F. So we'll come down here for our Reynolds number, which was 1.69 times 10 to the 6th, which is gonna rest like in here somewhere. And then our roughness factor is 2.5 times 10 to the negative 4. We got 2 times 10 to the negative 4, so probably be somewhere in there. It's okay if you're not exact for this. This is just to get us, you know, a rough estimate. Obviously this chart's, you know, pretty crazy and a lot of lines are overlapping, so just your best estimate. Usually on the FE, they're gonna say, you know, the question, the answer be like, what's the answer closest to, or whatever. They won't say like exact answer and stuff like that. So just your best guess is needed. I also just realized on this MOODy chart, it did give you that epsilon or whatever the fuck for the concrete right here. This gave it in millimeters though. We didn't want that though. We needed it in feet. So reference handbook. Okay, so I made the connection between these 2 points, which is here, and it doesn't fall on the lines of the MOODy chart, so we just need to, you know, get as close as we can, which looks to be about here. And if we follow that across, looks like 0.015 is what we're working with. So now that we have our friction factor, we can finally plug and chug. We have everything we need now. All right, so here's our equation again. Let's do it. So we found our friction factor to be 0.015. The length is 5,000 feet. Diameter is 4 feet. Our velocity that we found earlier, 5.97 feet per second over 2 times 32.2 feet per second squared. And we plug all that in, we get about 1.74 feet of head loss. So there you go. Try to get a little more in depth on that second one, because I mean the first one pretty easy. Yeah, just a little review of the Darcy-Weisbach equation, the MOODy chart, Reynolds number, things like that. Hopefully those helped, and hopefully I start making more consistent videos. So thanks, see you in the next one.